Hello everyone, welcome to VYAS Edification Quota. In this session, we are going to discuss NCERT and exercise solutions of chapter class 12th, chapter number 13 Nuclei. Clear? So definitely you will find detailed video solutions of each and every question, as well as you will find some key concept behind that question also. Clear? So now we are going to start all the solutions of this chapter and exercise solutions. So concentrate on a screen. So dear student, now we are going to discuss question number 13.1. So fully concentrate on a screen. In this question it is given to you, we have two parts, part number A and part number B. In part number A it is given to you two stable isotope of lithium, 6 lithium and 7 lithium has respective abundance of 7.5% and 92.5%. Clear? These isotopes have masses 6.01512 AMU and 7.01600 AMU. Clear? Now we have to find what is atomic mass of lithium. So now you can see in this question actually two isotopes of a lithium it is given to you, and actually our objective in this question is to find weighted average of lithium. Yes or no? So how can we find? Definitely because this lithium is present in the form of two isotopes and the percentage abundance is different. So how can we calculate? Definitely we have a very simple formula. So if we want to calculate atomic mass of lithium, so atomic mass of lithium. If we want to calculate atomic mass of lithium, how can we write? First of all, we will write atomic mass of this isotope 6Li6, 3Li6. So this is equal to, we can say 6.01512 multiplied with percentage abundance of this isotope. This is equal to 7.5% plus. Now you can see what is we can say atomic mass of this isotope. This is equal to 7.01600 and its percentage abundance it is given to you 92.5% and divided by. Now we will write total summation of percentage. So directly you can say this is 7.5 plus this is 92.5. Clear everyone? Now we will calculate. So we can write like this. Actually whenever we are calculating, this is weighted average. Yes or no? So weighted average it is given by, let's suppose if we take near about values, so 6.01. so let's suppose I am taking this is near about 6. Clear? So 6 multiply 7.5 means 15 by 2 plus. Now near about you can say this is 7 multiply 92.5. so 7 multiply 92.5 and you can say 92.5 divide by 10 and it is divided by 100. Clear? So now you can write like this. This is equal to 3. So we are getting that is 45 plus. Now if you multiply 925 with 7, so we can write it like this. 7 multiply 5, this is equal to 35. We have 3. So 14, 3, 17. We have 1. So 7 multiply 9, 63. So this is 64 and divided by 10 and it is divided by 100. So from that one we can write it like this. This should be equal to 45 plus 647.5 and it is divided by 100. Clear? So now if you add it, you will find this is equal to, we have 75 that is 12, we have 1 so 9 and we can say this is 6. Clear? So 692.5 and it is divided by 100. So we are getting average weight, or you can say average atomic mass of lithium. It is given by, this is equal to 6.925 U, or you can say this is atomic mass unit. Clear to everyone? Yes. Now we are going to discuss part number B. In the part number B, actually the same pattern of question we have, but values are changes. Clear? So now you can see boron has two stable isotope, boron 10 and boron 11. Clear? Their respective masses is also given to you. Okay. The atomic mass of boron is given to you in this question. It means weighted average of boron it is given So now we have to find abundance of 10 that is boron 10 and boron 11. Clear? So how can we calculate? We can write like this. Listen carefully. If we are talking about two stable isotope, clear? So let's suppose I am talking about this is boron 10 and let's suppose I am saying this is boron 11. Clear? So value of respective masses is given 10.01294. So 10.01294, clear? And for 11 boron we have 11.00931. This is given in terms of atomic mass unit. Clear? Now let's suppose I am assuming percentage abundance of this 10 boron, this is equal to x percent. So definitely you can say this is equal to 100 minus x percentage. Clear? And weighted average value, it is provided to you, this is equal to 10.811 u. Clear? So how can we write? Can we write like this? 10.811. Clear? This should be equal to now 10.01294 multiplied with x plus, now we can write it like this, 11.00931 multiply 100 minus x and divided by, now this is x plus 100 minus x. Clear everyone? So now from that one we can write it like this, x and x, this one is cancelled out. So if you multiply it with 100, you can write like this, 1081.1, this should be equal to 10.01294 multiplied with x plus, now this is what, 11.00931, this is 100 minus x. Clear everyone? So now definitely we can solve it. So if you solve, clear, you can write it like this, if you multiply 100 with 11, so it will be near about 1100.931. Clear? So we can write like this, 1100.931 minus 1081.1. Clear? And this should be equal to 11.00 x minus 10.01 and this is x. Clear? So if you subtract it, you will find this is equal to 8 point, this is what we can say 0 minus 1, that is 9. Clear? And from here we can say that is 1 and we can say this is 1. So this is 119.8. Clear? This should be equal to, now you can say we are getting this value 0.99x. Clear? So from that one, can we get value of x? Yes or no? Clear? Again I am saying this is what, 8, we have 9. So again we have 9, that is 1, and we can say at that time this becomes 0. So we are getting this is 19.8. Clear? 19.8. So now we can write like this, 19.8 divided by 0.99. So near about you can say this is equal to 1. So near about you are getting this abundance, this is equal to 19.8%. Clear? It means now you can say abundance of this stable isotope boron 10 that we are getting, this is equal to 19.9%. Clear? So what is the percentage abundance of this 11 boron? This should be equal to 100 minus 19.9. So now you can say this is near about 81, so 80.1%. Clear? Actually if you observe this question, directly you can say, if you are talking about atomic if you talk about atomic mass of boron, that is given to you 10.811, and this atomic mass is very near to this boron 11 atomic mass. It means the maximum percentage of boron isotope that we will get, this is equal to 11 boron. Yes or no? That's why atomic mass is coming near to this value. Clear? So this is all about this question. Clear? Now student, we are going to discuss question number 13.2. Clear? In this question it is given to you the 3 stable isotope of neon, 20 neon, 21 neon and 22 neon has respective abundance of 90.51%, 0.27% and 9.22%. Clear? The atomic masses of 3 isotopes are 19.99 atomic mass, 20.99 U and 21.99 U. Now we have to calculate what is average atomic mass of neon. Clear? So again a very simple question we have. First I am writing here all the data, so it will be definitely easier for you. So let's suppose first I am talking about 10 neon 20, clear. After that we have 10 neon, this is 21, clear. Then we have that is 10, this is neon, and that is 22, clear to you. So now you can say if we are talking about percentage abundance, it is given to you in this question, this is equal to 90.51, clear. Next we have 0.27, clear, and this is equal to 9.22, clear. And if we talk about atomic mass, if I am talking about atomic mass, it is given to you, this is equal to 19.99, 20.99, so 19.99, 20.99, and the last we have 21.99 U. Clear everyone? Yes. Now what is our objective? Our objective is to find average atomic mass of neon, clear. So how can we find? So let's suppose average atomic mass of neon, how can we write? We can write like this. Directly you can say, because percentage abundance of 20 neon is more, definitely we will find average atomic mass that is near to this, we can say 19.99 U. It means definitely you will find near about 20 point something U atomic mass, yes or no? So now let's calculate. So we can write like this, this is equal to first 19.99 multiplied with, this is 90.51 plus multiply 0.27 multiply 20.99 plus, now you can write like this 9.22 multiply 21.99 and divided by, now you have to add all the percentage abundance, this is equal to, you can say 90.51 plus 0.27 plus 9.22, clear. So now if you add and if you multiply and then if you divide with the total, so definitely if you add you will find this total is equal to 100, clear. So you can also write it like this. If we take some approximate calculation, definitely calculation is somewhat tedious. So what we can do, let's suppose assume this is equal to 20 multiply, let's suppose this is 90.5 plus, clear. Now you can say 0.27 multiply, this is 21 plus, now you can take 9.22 multiply 22 and it is divided by 100. So definitely now this calculation becomes easier, clear. So now if you multiply, how can you find? So if you find average atomic mass in terms of AMU, this should be equal to, now 20 multiply 90.5, so 90 multiply 20, that is directly you can say, if you remove this decimal, this one and this one cancelled out, so definitely you will get this value, that is 1810, yes or no. 905 multiply 2, this should be equal to 1810 plus, now if you multiply 27 with 21, 27 multiply 21 and it is divided by 100 plus, now you can also write it like this 9.22, so 922 multiply 22 divide by 100 and it is also divided by 100, clear everyone. So now 1810 plus, now if you multiply 27 with 21, how can you multiply? You can actually utilize Vedic mathematics. Directly you can say 1 multiply 7, we have 7, this is 2, and we can say 7 multiply 2 14, so 14 plus 2, this is 16 and divided by 4, so 7 6 and this is 5, it means we are getting 567. So 567 divided by, you can say 100, so 5.67 plus, now can you multiply 922 with 22? I am writing this side, 922 multiply 22, so that is equal to 4, clear. This is also 4 and we can say 18 multiply 4, this is 18, clear. So 4, that is 8, we can say that this is 8 plus 4, that is 12, we have 1, so 2 and we can say that is 10, we can say that is 1, so this one. Clear everyone? So 20, 28 and 4. So directly you can say 202.84 that we are getting. Clear? And it is divided by 100. Clear? So definitely we have some calculation, you have to simplify these calculations. Clear? So now if you add, how we can write, that is 5, and first of all I am writing it like this, 1810 plus 5.7 plus 202.8. Clear? Divided by 100. So 7 and 8, this is equal to 15. 15 we have 1. So 1 plus 5, 6, 6 and 2, that is 8. 1 and we can say that is 0. So 1, this is equal to 8 and plus 2, that is 10. So 2018.5 we are getting, and it is divided by 100. So final answer that I am getting, this is equal to 20.185 U. Clear? So definitely I already told you, because percentage abundance of this 20 neon is more, so definitely you will get the value near about atomic mass of this isotope. Clear? So correct answer of this question we have that average atomic mass 20.185 AMU. Clear everyone? So this is all about this question. So student, now we are going to discuss question number 13.3. In this question, our objective is to find binding energy in million electron volt of a nitrogen nucleus and atomic mass of nitrogen. It is given to you this value. Clear? Before solving this question, you should also know about what is mass of hydrogen and mass of a neutron. Clear? In terms of AMU. Clear? So now let us concentrate on the objective. Our objective is to find value of binding energy in million electron volt. So binding energy is actually given by binding energy, this should be equal to delta mc square. Clear? So now you can see, if you want to calculate binding energy, first of all we have to calculate mass defect. Clear? So now you can say, sir, from where we are getting this mass defect? So listen very carefully. If I am talking about this 7 and 14, so in this we have 7 proton plus 7 neutron. Clear to everyone? So definitely 7 proton and 7 neutron, when they combine, they form, we can say that is nucleus of this nitrogen. Clear? So at that time I can write like this, mass of reactant. Mass of reactant, this is given by 7 times of mass of proton plus 7 times of mass of neutron. Clear? Now definitely when 7 proton and 7 neutron combine, they form nucleus of nitrogen. So this is atomic mass is given to you. Now listen very carefully. Whenever we are calculating mass defect, delta M, we will write like this, mass of reactant minus mass of product. Clear? So definitely you can say when 7 proton and 7 neutron are combining, they are getting a nucleus of nitrogen. Clear? So now we can write like this, this should be equal to 7 MP plus 7 Mn minus. Clear? Now what is the atomic, what is the nucleus? So now we will write mass of a nucleus of 7 and 14. Clear? So in this question, whatever is given to you, this is atomic mass, and in this atomic mass, mass of electron is also included. So what we have to do, actually we will subtract mass of electron from this atomic mass. After that we will get mass of nucleus of nitrogen. Clear to everyone? Yes. So now I can write like this, delta M, this should be equal to 7 MP plus 7 Mn. Mn means mass of neutron. Clear? Now minus, now I can write like this, this is atomic mass of 7 and 14. Clear? Minus the number of electrons is equal to number of protons. So now we can write like this, this is 7 times of Me. Yes or no? So now we can write it like this, 7 MP plus 7 Mn minus, this is what we can say atomic mass of nitrogen 7 and 14 plus 7 times of Me. Now it's a general common observation. If you write 7 times of MP plus Me, clear? So if you add mass of proton and mass of electron, you will get this mass near about mass of a hydrogen, clear, and mass of hydrogen value it is written here 1.00783, clear. So you can write like this, plus 7 Mn minus mass of 7N, this is 14, clear. So now you can also write it like this, 7 times of mass of hydrogen plus mass of neutron minus mass of, we can say this is actually atomic mass, clear. So now you can place all values so that you can get value of mass defect, clear. So actually our objective is to find binding energy in nucleon, binding energy in the million electron volt. So how can we calculate? Actually we know this is delta mc square, clear. Definitely this energy we will get in joule, but if we want to convert this into electron volt, clear. So we can write like this, if we multiply this mass defect with 931.5, then definitely we will get this answer in million electron volt, clear. So now mass defect that I am getting, I am writing all these value, 7 into value of mass of hydrogen is given 1.00783, clear. So 1.00783, clear, then plus, now 7 multiply, what is mass of neutron 1.00867, so 1.00867, clear, then minus what is atomic mass. So atomic mass it is given to you 14.00307, so 14.00307, and if we multiplied it with 931.5, then definitely we will get this answer in million electron volt, clear to everyone. So now if you calculate it, can you calculate? Yes. So first multiply it with 7, clear. So directly you can say, if you multiply it, first multiply, then 8 and then subtract it, and then multiply it with 931.5 million electron volt, clear. So at that time you can get this value near about 104.66 million electron volt, clear, 104.66 million electron volt, clear. So like this you can calculate binding energy in million electron volt, and we are getting this binding energy. Why? Because there is a mass defect, and due to mass defect you are getting this is binding energy. Binding energy is basically the energy that is required to hold proton and neutron in the nucleus. Let's suppose if we want to separate proton and neutron, then definitely we have to provide some external agency, external energy, or we have to do some work if we want to separate proton and neutron, clear. So like this you can calculate value of binding energy, clear. So this is all about this question. Now student, we are going to discuss question number 13.4. In this question our objective is to find binding energy of nuclei, iron and bismuth in the units of million electron volt from the following data, and atomic mass of iron as well as bismuth it is provided to you, clear. So now definitely whenever I am talking about binding energy, means definitely first our objective is to find mass defect, clear. So first of all I am talking about number 1, that is iron, clear. So first we are talking about this 26 Fe56, clear everyone. So now can you tell me number of proton and neutron in this we can say that is nuclei. So directly you can say proton we have, this is equal to 26 plus, now if we are talking about neutron is equal to 56 minus 26. So in the nuclei of iron we have total 26 proton plus we can say 30 neutron, clear. So if I am talking about mass of reactant, so mass of reactant that I am getting, this should be equal to 26 times of mass of proton plus 30 times of mass of neutron, clear to everyone. But now definitely when they combine they will form a nuclei of iron, clear. So can we find mass of product, clear. So mass of product we can write it like this, this is atom, actually we need mass of nuclei of iron, clear. So mass of nuclei of iron, and this is 26 Fe, we can say 56, clear, and this should be equal to, you can write like this, because atomic mass is given to you, you have to subtract mass of an electron, after that you will get mass of this nuclei, clear. So you can write it like this, mass of 26 iron 56 minus, now we have number of electrons equal to number of protons, clear. So directly you can write it like this, this is multiplied with 26 times of mass of electron, clear. So now can we find mass defect? Yes, we can easily find mass defect, delta m. Delta m, this should be equal to, first of all I will write mass of reactant. Mass of reactant we have 26 mp plus 30 mn. Now I am subtracting mass of a product. So mass of product we can write it like this, m, this is atomic mass. So 26, this is iron and this is 56, clear, minus 26 me, mass of electron, clear. Now again you can see, if you open it, you will find this delta m, this should be equal to 26 mp plus me plus 30 mn minus atomic mass 26 Fe, this is 56, clear. Now you know, if you add mass of proton and mass of electron, it will be come out near about mass of hydrogen, clear. So you can write like this, 26 mass of hydrogen plus 30 mass of neutron minus m, this should be equal to 26 Fe, that is 56, clear to everyone? Yes. Now you can place all the values and easily you can get value of mass defect. So delta m, this should be equal to 26 multiply, what is value of mass of hydrogen? Mass of hydrogen value we have 1.0078 amu plus, now what about mass of neutron? So 30 multiply 1.0086, clear. Then we have to subtract minus atomic mass of this iron, so this will be equal to 55.9349, so 55.9349, clear to everyone? So now if you multiply it, and then subtract it, clear, definitely you will get mass defect, this is equal to 1.7, this is equal to definitely mass defect you will get, this will be equal to if you multiply near about, if you multiply you can say 26 multiply 7, this should be equal to, we have 42, we have 4, so now you can say 7 multiply to 8, that is 14 plus 4, this is equal to 18, clear. So now we can say this is 18, this is 0, so 26.082 plus, similarly you can see if you multiply it with 30, you can see 30 point, now you can say this is 024 near about and 55.9349, clear. Now you can add it and you can subtract it with minus 55 point something, and definitely you will get mass defect. So mass defect value you will get near about 0.52, 0.528461, clear everyone? Now but what is my objective? My objective is to find binding energy. So binding energy we can write it like this, this should be equal to delta mc square, clear. But we need this binding energy in million electron volt, so at that time we can write it like this, 0.528461 multiply 931.5, and this will come out to be in the terms of million electron volt, clear. So now this is definitely 0.528 near about 1 by 2, yes or no? So if you solve it, you will find this value will come out to be 492.26 million electron volt, clear. So like this you can calculate value of binding energy, clear, for the nucleus. Which nucleus? For the iron, clear. Now similarly we have to find binding energy for this we can say nuclei, that is bismuth, clear. So now concentrate. Now if I talk about part number B, so in the part number B we have this nuclei 83 bismuth 209, so 209 Bi, and this is 83. Now in this we have number of protons, this is equal to 83 proton, plus what about total number of neutrons? This will be equal to 209 minus 83, and this will be neutron. Clear? So now we can see total we are getting 83 proton plus this will be 6, and we can say 126 neutron. Yes or no? Clear. So now again can we write mass of reactant? So mass of reactant that I am getting, this is equal to 83 times of mass of proton plus 126 times of mass of neutron. Clear? Again we will find mass of product. Clear? So mass of product, this should be equal to mass of product. Mass of product means definitely this mass that is given to you, this is atomic mass, but if you want to find mass of nuclei of bismuth, definitely you have to subtract mass of electron. Yes, so we can write it like this. This is mass of, we can say this is 83. Yes, 83 bismuth. This is 209, and definitely this should be equal to. Now actually we want to find mass of a nuclei, so this should be equal to atomic mass 83 Bi 209. Now we have to subtract mass of electron, so number of proton is equal to number of electrons, so this should be equal to 83 times of mass of electron. Clear? So now you can see if you write expression of binding energy we have, this is given by delta mc square. Clear? But if you want to find this binding energy in terms of million electron volt, so this should be equal to, now 83 mass of proton plus we can see this is 126 mass of neutron minus then 83, this is bismuth 209 plus this is equal to 83 Me. Yes or no? Now you know if we write this like this 83 Mp plus Me, so mass of proton plus mass of electron, this will be come out to be near about mass of hydrogen plus 126 mass of neutron minus this is atomic mass 83 Bi, this is 209. Clear to everyone? So now from this one we can write value of binding energy. Clear? Actually this is just the mass defect, you have to multiply it with C square or with the 931.5 million electron volt. Clear everyone? Yes. So now we can place all the values, so it will be equal to 83 multiply. What about mass of hydrogen? This will be 1.0078 plus this should be equal to 126 multiply. What is mass of neutron? This will be 1.0086. Clear? Minus, now atomic mass unit, it is provided to you 208.9803. So 208 point, this is 9803. Clear to everyone? So definitely again we have to do some calculation this side, and if you multiply this with 931.5 million electron volt, you will get your binding energy. Clear? So if you solve it, clear, you will find this value 1640. You will get 1640.26 million electron volt. Clear to everyone? Million electron volt. So like this you can calculate we can say binding energy for two different nuclei by considering mass of hydrogen, mass of neutron and atomic mass of particular we can say that is nuclei. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 13.5. Clear? In this question it is given to you, a given coin has a mass of 3 gram. Calculate the nuclear energy that would be required to separate all the neutrons and proton from each other. It means the total energy that is required to separate proton and the neutron. It means we are talking about binding energy. Clear? So now for you actually for simplicity you can assume that coin is actually made up of this copper atoms. Clear? And its atomic mass is given to you. Clear? So definitely first objective is to find binding energy, and for binding energy we need mass defect, clear. So directly you can write like this. First of all, 29 copper 63, number of protons in copper we have 29 proton, plus if we are talking about 63 minus 24, this is we can say number of neutrons, clear. So from that one you can see we have total 29 protons plus directly you can say 63 minus 29, so this will be 34 neutrons, clear, 34 neutrons, clear to everyone? Yes. So now can we find first mass of reactant? Mass of reactant, mass of reactant means we can say 29 multiply mass of proton plus 34 multiply mass of neutron, clear. Now you can say mass of reactant, this one, and mass of product, clear. Mass of product that I am getting, this will be equal to, directly you can say this is equal to atomic mass, clear, but actually you need nucleus, actually mass of a nucleus that is formed. So mass of nucleus of 29, this is copper and this one is 63, clear. And how can we get it? Actually if you want to find mass of nucleus, definitely you have to subtract mass of electron. So directly you can write like this, mass of we can say that is atomic mass, this is equal to 29 copper 63 minus, clear, minus, now we have this is equal to total number of electrons, total number of electrons is equal to total number of protons, so 29 Me, clear. So from that one you can get mass defect. So mass defect delta M that you are getting, this is equal to mass of reactant minus mass of product, clear. So mass of reactant that you are getting, this will be equal to 29 MP plus 34 Mn minus, what about mass of product? Mass of product that you have M, you can see 29 we can say copper 63, clear, plus 29 mass of electron. Now you can see if you add mass of proton plus mass of electron, this will be near about mass of hydrogen, clear. So now we can write it like this, 29 Mh plus 34 Mn minus M, this will be equal to 29 copper 63, clear. So from this one you can easily find mass defect, but our objective is to find value of that is binding energy. So directly first you can write all these values, 29 into 1.0078 plus this one is what, 34 1.0086 minus, now atomic mass of this copper, it is provided to you 62.9260, clear. So from that one we can write value of delta M, mass defect. Definitely if you calculate you can easily find this value of delta M, and this delta M that you are getting, this will be near about 0.592225, yes, 0.59225, clear. But our objective is to find binding energy. So binding energy we can write delta E, this should be equal to delta MC square, clear, 0.59225 multiply. Now we can convert this into million electron volt, clear. So now you can say this is near about 60% of 931.5. So if you calculate you will find this value 551.50 million electron volt, clear. Now listen very carefully, this is binding energy of one nuclei, yes or no? This is binding energy of one nuclei, clear. But actually it is given a coin is having mass 3 gram, clear. So directly you can see when a coin is having a gram, that is 63 gram, clear. So if I am talking about 63 gram, it means I am talking about 1 mole, clear. 1 mole means the total number of atoms that is present, it is equal to Avogadro number, clear. So from that one we can write 1 gram, this should be equal to Na divided by 63, clear. But we have a coin of 3 gram. So what is total number of atoms that is present? So 3 gram, this should be equal to Na divided by 63 multiply 3, this should be equal to Na divided by 21. Clear? So now you can see Na means Avogadro number, and this should be 6.023 into 10 to the power 23 divided by 21. Clear? So from that one you can find number of atoms that is present. Clear? So number of atoms you will find this is near about 2.868 into 10 to the power 22. Clear? Yes or no? So now you can say, if we are assuming definitely this much amount of atoms that is present in 3 gram of coin, and each atom contains 1 nuclei, so can we find the total binding energy? Clear? So yes, so directly we can say energy required to separate proton and neutron, and that is given by number 1. First we have 551.50 million electron volt energy that is required for 1 nuclei. Clear? But we have this much amount of number of atom, so 2.868 into 10 to the power 22. Clear? So if you calculate, easily you can get final value of that is you can say, you can write it like this: 551.50 million means 10 to the power 6 multiplied 1.6 into 10 to the power minus 19, you can convert this into joule. Clear? And it is multiplied with 2.868 into 10 to the power 22. Clear? So now we can calculate what is total energy required. If you solve it, you will find this value near about 2.533 into 10 to the power 12 joule. Clear? Definitely there is some calculation is to be there, you can take some approximation and you can get approximate result. Clear? So this is final value, final energy that is required that we got here. Clear? So this is all about this question. So dear student, now we are going to discuss question number 13.6. This question is actually based on the properties of alpha particle, beta particle and so on. Clear? So now fully concentrate on a screen. In this question it is given to you, we have to write nuclear reaction for number 1, whenever we have nuclei of radium and there is an alpha decay is to be taking place. Clear? So first of all let us try to understand number 1, whenever we are talking about alpha decay. So let's suppose if I am representing this by ZXA, whenever there is an alpha decay, there will be decrease in the number 2 with the atomic number Z minus 2. Let's suppose that is Y, and there is decrease in atomic we can say that is mass number, this is equal to 4 plus you can write this is equal to twice He 4. Clear to everyone? So according to this given question, we have this nuclei that is 88, this is radium. Clear? And we can say this is 2 to 6. Now whenever we have alpha particle emission means I can write it here, this is 86. Now definitely one substance will form. Now you know atomic number 86 we have, that is known as radon. Clear? And we have here this is 222 because there is a decrease in a 4 in the mass number. Clear to everyone? Yes. So this is what? This is known as radon, and we have this one is that is radium. Clear? Yes or no? Yes. Now we are going to discuss second one. In the second one again an alpha decay is to be taking place for the nuclei, that is plutonium 94 and this is 242. So definitely there will be decrease in atomic number by 2. So 92. Now you can say definitely 92 atomic number we have for uranium and this will be 238. Clear? And definitely there will be this one 2He4. Clear? So this one. Clear? This is what? That is plutonium. Clear everyone? Yes. Now we are going to discuss third one. Actually we have beta minus decay of phosphorus. Clear? So now actually whenever we are talking about beta minus decay, clear? So whenever I discuss beta minus decay, clear? In beta minus decay always keep in mind that suppose we have ZXA, so definitely because we have beta minus decay, so atomic number increases by 1, so this is 1, clear, plus now you can write this is minus 1 E0, there is no change in a mass number, clear, plus definitely antineutrino particle will be emitted, clear. So now how can we write the equation number 3 for phosphorus? So phosphorus 1532. So now you can see it is increases by 1 atomic number, so definitely we will get here sulfur, that is 32, plus minus 1 electron 0, plus we have antineutrino. Clear to everyone? Yes. Now if I talk about number 4th, and number 4th again we have beta minus decay. So number 4th beta minus decay for nuclei, that is 83 bismuth 210. So 210 bismuth, this is 83, clear. So now whenever I am talking about beta minus decay, definitely you can see atomic number increases by 1, clear, and mass number remains same. So 84 is having that is element 84 is for, we can say that is polonium, that is PO, yes or no, clear. This is for polonium, and we can say 1 electron is released, that is the minus beta particle, and plus we have antineutrino. Clear to everyone? So like this you can write nuclear equation like this, clear. Now if we talk about number 5th we have beta plus decay, means positron, clear. So beta plus decay of 6 carbon 11. So now listen carefully, whenever we have beta plus decay, so let's suppose we have ZXA and we have beta plus decay, means atomic number is decreases by 1, this is Y, clear, and there is no change in a mass number, plus you can say the positron is emitted, and definitely we can see neutrino, clear, and neutrino particle is also emitted, clear. So now you can say if we talk about this question 6C, we have carbon 6C11, so 6C11 atomic number decreases by 1, so definitely 5 is atomic number for boron, clear, 11 plus 1 E0, and we have this is neutrino, yes or no, yes, clear. Now we are going to discuss equation for number 6. Number 6 we have, that is beta plus decay for 43 Tc. Tc means we can say that is technetium, clear. So now you can see definitely we need some help from periodic table so that we can find this element. So number 6 we have, that is 4397. So 43 Tc, that is 97. Whenever there is a beta plus decay means this become 42, clear, and 42 is the atomic number for molybdenum, clear, and this one we have 97 plus, clear, because we can also write plus 1 E0, and this is neutrino. Clear to everyone? So like this you can write equation, nuclear equation for all the 6. Now we are talking about electron capture. Electron capture means to absorb electron, clear. So at that time what will happen, we have nuclei of xenon, so number 7th, clear. Now 54 Xe 120, 54 Xe 120, clear, 54 Xe 120. So in this case I can say 54 Xe 120 electron capture I am talking about. So now electron capture means definitely one electron is adding here, clear. So now we can say electron capture minus 1 plus you can say minus 1 E0. So definitely you can say again an atomic number, it is decreases by 1, so it will be now 53. 53 is having atomic number for iodine, clear. So 53 iodine for 120, there is no change in a mass number. Yes, definitely a neutrino particle which also emitted, clear. So like this you can write all the nuclear equation, clear, and definitely you get some idea what will happen in an alpha decay, positron means beta plus decay, beta minus decay, clear, and what will happen in an electron capture, clear. So this is all about this question. Now dear student, we are going to discuss question number 13.7. This is a question related to radioactivity. So a radioactive isotope has a high half-life of T years, capital T years, it is given to you. How long will it take the activity to reduce to number A 3.125%, second one 1% of original value. Clear to you? So now concentrate. So now it is given in this question, we are having time period, or we can say that is the half life. This half life is equal to capital T. Clear? Now we you know one relation that is very important relation of an activity. So activity A at any instant, it is given by A naught e to the power minus times of lambda, and we can say that is equal to T. Yes or no? Clear? Similarly, you can write the number of nuclei that remains undecayed. It is given by n equal to n naught, clear, e to the power minus times of lambda T. Yes or no? So now if you divide it, you can write like this, A by n, this should be equal to A naught divided by n naught. Clear to you? So now we can write it like this, this is what A divided by A naught, this should be equal to n divided by n naught. Clear to everyone? Yes or no? Yes. So now from here you can see, actually we know one relation, that n is given by n naught 1 by 2 power, that is T divided by T half. Yes or no? Clear? So at the time you can write like this, n by n naught, this should be equal to 1 by 2 power n. Clear? And n is given by, that is time T divided by half time, half life period. Clear? So now can we write it like this, n divided by n naught, this should be equal to 1 by 2 power T divided by capital T. Clear to you? So now in the first part, I am talking about first part. In the first part it is given to you the number of the activity. So the activity is reduces to 3.125%. Clear? So definitely activity ratio is the same as the ratio of number of nuclei that is remain undecayed. Clear? So at that time I can write it like this, this should be equal to 3.125 percentage. So 3.125% of n naught. So we can write it like this, this is n naught. Clear? And it is divided by, that is 100, and initial number of nuclei we have n naught. Clear? 1 by 2. What about time T? This is our objective. So time T and half time period, it is given to you, that is capital T. Clear? So from that one you can write it like this, n naught and n naught, this one is cancelled out. So you can write it like this, 1 by 8 divided by 100, this should be equal to 1 by 2 power, that is T by capital T. Clear? So now if you multiply 3 with 8, so that is 24. So 25 divided by 8 multiplied with 100, and this should be equal to 1 by 2 power T by capital T. Clear? So from that one we can write it like this, this is equal to 4. So 1 by 32. 1 by 32 we are getting, this is equal to 1 by 2 T by capital T. Clear? Now you can write 1 by 32, this should be equal to 1 by 2 T by capital T, this should be equal to 1 by 2 power 5. Clear? So from that one you can write it like this, T by capital T, this should be equal to 5. So we are getting small t, this is equal to 5t. Clear? So this is the total time taken. This is with this time will be 5 times of a half life period when the activity is reduces to 3.125%. Clear everyone? Yes. Now if I am talking about part number B, it is given this activity is reduces to 1% of its original value. Clear? So it means I can write it like this, that is equal to 1 divided by 100 n naught divided by n naught. Clear? Yes or no? And we can say this should be equal to, or this should be equal to 1 by 2 power, that is T by, we can say that is T half. Clear? So from that one you can write like this, this is equal to 1 by 100, and this is equal to 1 by 2 power T, and that is T half. Clear? So now you can say that is T half. Clear? So actually you can also write this expression like this, so it will be better for you, n equal to n naught e to the power minus times of lambda T. Clear? So from that one, this is equal to n naught by 100, this is equal to n naught e to the power minus times of lambda T. Clear? So N naught and N naught, this one is cancelled out. So 1 by 100, this should be equal to e to the power minus times of lambda t. Clear? So e to the power lambda t, this should be written as 100. Clear? Now if I am taking log both side, then we can write it like this: lambda t log base e, and you can say this should be equal to natural log, and that is 100. Clear? So from that one you are getting value lambda t, this should be equal to 2.303, and we can say that is log base 10, and that is 100. Clear everyone? So now can we find value of time t? Yes, time t, it can be written like 2.303, and we can say multiplied with 2. Clear? And it is divided by lambda. Clear? So how can we write value of lambda? Clear? How can we write value of lambda in terms of half time period? Clear? So actually you know t half, it is given by 0.693 divided by lambda. Clear? So instead of lambda, now I can write this is 0.693 divided by t half. Clear? So value of t, that I am getting 2.303 multiply 2 and multiply. Clear? So lambda is given to you, this is divided by 0.693. Clear? And we can say this is equal to t half. T half is equal to, that is capital T. Clear everyone? So now if you solve it, you will find this value is equal to 6.65 times of capital T. Clear? It means you can see this activity remains 1% of original activity when time t equal to 6.65 t. Clear? So this is all about this question. Now dear student, we are going to discuss question number 13.8. Clear? Actually this is a very interesting question. Why? Because in this question a method is given to you. How can we determine the age of a particular substance that we are finding? Let's suppose if we are talking about Indus Valley civilization. Clear? So in that one, let's suppose if I am talking about Mohenjo-daro. Clear? And let's suppose we are getting some let's suppose ornaments, and let's suppose we are getting some dead animals, and let's suppose we are interested that this is actually what is the time period of this particular thing. Clear? So actually we can find this by the help of a method that is known as carbon dating method. Clear? So this question is fully based on that particular process, so concentrate fully on a screen. In this question of 13.8, it is given to you the normal activity of living carbon containing matter is found to be 15 decays per minute for every gram of carbon. Clear? Second, this activity arises from the small proportion of radioactive 6C14 present with the stable carbon isotope, that is 6C12. When the organism is dead, its interaction with the atmosphere which maintains the above equilibrium activity cease, and its activity begins to drop. Okay, from the non half life of carbon 614 and the measured activity, the age of specimen can be approximately estimated. Okay, fine. This is the principle of carbon 1614 dating used in the archaeology. Suppose a specimen from Mohenjo-daro gives an activity of 9 decays per minute per gram of carbon. Clear? Now we have to estimate the approximate age of Indus Valley civilization. Clear to you? So now you can say initially when we are talking about normal activity. So if you are talking about normal activity, it is given to you 15 decays per minute for every gram of carbon. Clear? So from that one we can write activity at time t equal to 0, this is 15. You can say this is disintegration per second. Clear? And we can say that is per gram of carbon. Clear? Now it is given that we have to find at what time the activity remains 9 decays per minute per decays per minute. Yes, decays per minute per gram. Clear? So at that time you can write it like this: A, capital A, it is given by, that is 9. We can say this is disintegration per minute, and this is per gram. Clear to you? So now actually we know one formula, and that formula is A equal to A naught. We can say that is 1 by 2 power T divided by that is T half. Clear? So now you can say what is value of A we have, that is equal to 9. This should be equal to 15, and 1 by 2 power T divided by, now we can say that is, let's suppose I am indicating half life is by a term that is capital T. Clear? So now you can say 9 by 15, this should be equal to 1 by 2 power T by capital T. Clear? And this should be equal to 3 by 5. Clear? So now from that one, if you write 1 by 2 power that is T by capital T, this should be equal to 3 by 5. Clear? So if I am taking log, so I can write it like this, T by capital T log that I am taking base E. Clear? So this will be 1 by 2 equal to natural log, we can say that is 3 by 5. Clear? So from that one I can write it like this, minus T by capital T log base E 2, this should be equal to log base E 3 minus log base E that is 5. Clear? So from that one can we write like this, T by capital T, this should be equal to, actually can we convert this into base of a 10? Yes, that is 2.303. Now base log base 10, that is 3, you can say that is 5 first, because we are also multiplying with the minus. Clear? Yes. So that is 5 minus log base, this is 3, yes or no? Clear? And it is divided by, that is 2.303 log base 10, that is 2. Clear? This one and this one cancelled out. Now definitely you know what is value of log 5, this is equal to 0.699. Yes. What about value of log 3? Log 3 value we have, this is 0.4 and that is 77. Clear? And what is value of log 2? Log 2 value we have 0.301. 0.301, and we can see we are calculating value of time t, so it should be multiplied with the half life. Clear? So from that one we can write it like this, value of t. Now if you calculate, first of all you have to subtract with 0.699 minus 0.477, it should be divided with 0.301. Clear? So now if you solve it and then if you multiply it with capital T, this capital T is equal to, now what is half life that is provided to you? Half life is given to you 5730 years. Clear everyone? 5730 years. Clear? So now you can see we can write like this, 57 that is 30. Yes or no? Yes. So if you solve it, definitely you will find the total time taken, or we can say we can find the total time before which the activity of this particular is to be 15 disintegration per minute. Yes. So now we can say this time if you calculate, you will get this is equal to 4224 years. Clear? 4224 years. Clear to everyone? So this is all about this question. Now dear student, we are going to solve question number, that is 13.9. Again this question is related to activity, or we can say radioactivity. Clear? So now concentrate. In this question it is given to you, obtain the amount of 27 cobalt 60 necessary to provide a radioactive source of 8 millicurie strength. Okay, the half life of 27 cobalt is 5.3 years, it is given. So now you can see actually value of activity is given to you in this question, but this activity is not in a disintegration per second or in a term of a becquerel. Clear? So now what we can do, actually we can write it like this. Clear? So now if I talk about activity A, it is given to you 8 milli. So first we can convert this into multiplied with 10 to the power minus 3, and now you can say 1 Ci. Can we say 1 Ci equal to how many disintegrations per second? Clear? So you can say it will be equal to 3.7 into 10 to the power 10. This is disintegration per second, or you can say directly becquerel. Clear? So now if you multiply, you can say 8 multiply 3.7. So we can say that is 6. We have 5. So that is 29.6 into 10 to the power 7 and this is becquerel. Clear? So now we can say this is activity A. Clear? Activity A equal to 29.6 into 10 to the power 7 becquerel. Clear everyone? So now this is value of A we have. Clear? But what is my objective? My objective is to calculate the amount is necessary to provide a radioactive source. Clear? Actually you know one relation. What is that relation? That relation we have A should be equal to lambda times of n. Clear? Now we can write this lambda in terms of we can say that is half life. So 0.693 divided by we can say that is half life, that is T half. Clear? Multiplied with n. So from that one can we find the total number of atoms that is present? Yes, we can write like this, capital N, this should be equal to A multiply that is T half divided by n equal to A multiply T half divided by 0.693. Clear? So now you can write it like this, value of A we have 29.6 into 10 to the power 7 multiply. What about half life? Half life is given to you in years, so 5.3. Now you can convert this years into seconds. Clear? How? In 1 year we have 365 days, in 1 day we have 24 hours, and in 1 hour we have 3600 seconds. Clear? And it is divided by now 0.693. Clear? So from that one can we calculate total number of atoms that is present? Yes or no? Yes. So from that one now we can write like this, 29.6 into 5.3 into 365 into 24 into 36 into 10 to the power 9 divided by 0.693. Definitely we have some tedious calculation here, but definitely we have to do it. So directly I am telling you what is value of capital M that I am getting. Clear? So capital N value you will get, this is equal to 7.15 into 10 to the power, clear, 7.15 into 10 to the power 16 atoms. Clear? Now listen carefully, what is our objective? Objective is to find the amount of 27 cobalt 60 to provide a radioactivity of this strength. Clear? Now how can I calculate? Clear? So very simple calculation we have. If I am talking about 27 cobalt 60, now directly you can say if I am talking about 60 gram, so in 60 gram we have total Avogadro number atoms. Clear? Because this is equal to 1 mole. Clear? So from that one we can write it like this, 1 gram, this 1 gram should be equal to Na and it is divided by that is 60. Clear? So 1 gram should be equal to Na divided by 60. Clear? Now if I am talking about, clear, so now you can see actually we have to find the total mass. Clear? So can we write it like this? Let's suppose we have total Na number of atoms, then we have total mass that is 60 gram. Clear? So when we have only one atom, clear, at that time we can say this is equal to 60 divided by Na. Clear? Now you have the calculation, and in calculation you have the total number of atoms present, and this is equal to 7.15 into 10 to the power 16. Clear? So when we have 7.5 into 10 to the power 16 atoms, clear, so at that time I can write it, this is 60 divide by, now we have that is Na multiply 7.5 into 10 to the power 16 atoms. Clear? So now we can write it like this, what is this value? This is equal to 60 divided by, now what is value of Avogadro number? 6.023 into 10 to the power 23 multiplied 7.5 into 10 to the power 16. Clear? So from this one if you calculate, clear, from this one if you calculate you can find value of that is the mass. Clear? And mass value definitely you will get near about, this is equal to 7.123 into 10 to the power that is minus 6 gram. Clear everyone? Definitely you can take some approximation, this is 16 and we can say 10 to the power 23, so we are getting 10 to the power minus 7. Clear? Near about this is 10, so definitely we will get this value near about 7.123 into 10 to the power minus 6 gram. Clear? So from this question what we are learning? Clear? Actually this much amount of this 27 cobalt 60 is required if we want to provide a radioactive source of this much of strength. Clear to everyone? So this is all about this question. Clear? Now dear student, we are going to discuss this question number 13.10. Clear? And in this question it is given to you the half-life of strontium 90, it is given to you, that is 28 years. Clear? So now I can write it like this, that is T half is given by, that is equal to 28 years. Clear? What is the disintegration rate of 15 milligram of this isotope? Clear? Now let us try to understand the concept of this question with very basics. Clear? Now you can say from this nuclei, you can say that is 38 strontium 90. Clear? Now directly you can say when we have 90 gram at that time total number of atoms that is present, it is equal to Avogadro number. Clear? So if I am talking about 1 gram, clear? So in 1 gram we have total number of atoms that is present, Na divided by 90. Clear? Now it is already given in this question, we are using 15 milligram of this isotope. Clear? So in 15 milligram means 15 into 10 to the power minus 3 gram. Can we find the total number of atoms that is present? Yes. So total number of atoms present, Na divided by 90. Clear? And multiplied with 15 into 10 to the power minus 3. Clear? So from that one you can see this is 6. So I am getting value of capital N, means total number of atoms present in the 15 milligram of this sample. Clear? So it will be written like this, 6.023 into 10 to the power 23 divided by, now this is 6 multiply 10 to the power minus 3. So near about you can say, if we cancel this is near about 1, so it will be equal to near about 10 to the power 20. Clear? 10 to the power 20 atoms present. Clear? Now we can say, now you can say actually what is disintegration rate that we have to find. So actually we know one important relation, that activity is given by product of N and multiplied with lambda. Clear? So this activity is measured in terms of disintegration per second or in a becquerel. So value of N, we are taking 10 to the power 20, but how can we calculate value of lambda? Lambda value is calculated by a simple formula, 0.693 divided by, that is we can say T half. Clear? So now I can write it like this, A equal to 10 to the power 20 multiply 0.693 divided by, what is T half? T half means half-life. Half-life is given to you 28 years. Clear? So first you have to convert this year into number of days, then we can convert in number of hours, then we can convert this into number of seconds. Clear to everyone? Yes. Now we have a simple calculation. We can write it like this, 693 multiply 10 to the power 17 divided by 28 into 365 into 24 into 3600. Clear to everyone? So from that one we can find value of activity. Clear? So now if you solve it you will find this value near about 7.83. Clear? 7.83, or if you calculate exactly you will find this value 7.77 multiply 10 to the power 10. Definitely somewhat calculation we have to do, but final result we have 7.877 into 10 to the power 10, and this is, we can say, disintegration per second, or you can say in terms of becquerel. Clear? So can we convert this into in the terms of a Curie? Yes. So actually if we want to convert this activity in a Curie, we have to divide this activity 10 to the power 10 with the, now actually we know one relation, this is equal to 3.7 into 10 to the power 10, then after that we will get this answer in terms of Curie. Clear? So definitely if you solve it, you can say this one and this one is cancelled out, and near about this value we are getting 2 point something. Clear? So final answer that I am getting for this question, 2.13 Curie. Clear to everyone? So now you can say actually what we are understanding from this question, that is very important, the disintegration rate of this 15 milligram of this isotope, that is equal to 2.13 curie. Clear everyone? So this is all about this question. Clear? Now student, we are going to discuss this question number 13.11. Clear? In this question we have to find ratio of nuclear radius of gold isotope and silver isotope. Clear? So dear student, definitely you know one relation between the radius and the mass number. Clear? And that relation is given by R. This should be equal to R naught a to the power, that is 1 by 3. Clear? This relation is given to you, R equal to R naught a to the power 1 by 3. Clear? So now you can see, if I am talking about radius of we can say that is gold and corresponding radius for silver. Clear? So from that one you can say this R naught value we have constant, and this R naught is near about, that is 1.2 for me. Clear? So R naught. Now what about the mass number? Mass number of this gold, that is we can say 197, and its power we have 1 by 3. Clear? Divided by R naught. Now what is mass number for this silver? For silver we have 107 power 1 by 3. So now I can say R naught and R naught, this one is cancelled out, and this should be equal to 197 divided by 107 and its power, that is equal to 1 by 3. Clear? So near about, if you solve it, definitely you can say this is near about 2, and if you take the 2 power 1 by 3. Clear? So this ratio of radius you will get, this is equal to, and we can say near about, that is equal to 1.23. Clear? This ratio that I am getting, that is equal to near about 1.23. Clear to everyone? Clear? So let's suppose if I ask to you one more question. Clear? Let's suppose if I ask, find the ratio of nuclear density of both isotopes. Clear? It means I am asking to you radius, that is density, nuclear density. I am just talking about nuclear density, not mass density. So nuclear density of gold over nuclear density of silver. Clear? If you have some knowledge of this chapter, definitely you can say, sir, nuclear density does not depends on the, we can say, radius, because it does not depends on a radius. Clear? So at that time directly you can say this ratio we are getting 1:1. Definitely we have derivation of this question also, but directly you have to write, if I am talking about gold nucleus, if I am talking about silver nucleus, always keep in mind its nuclear density always remains same, because it does not depends on the size of nuclei. Clear? So directly keep in mind nuclear density does not depend on the size of nuclei. Clear everyone? So directly correct answer for this ratio we have, that is 1:1. Clear everyone? So this is all about this question. So student, now we are going to discuss question number 13.12, and this question is related to alpha decay. Clear? In this question it is given to you, we have to find the Q value and the kinetic energy of emitted alpha particle in the alpha decay. Clear? So now two situations are given to you. First, this is the nuclei 88 radium 226, and second nuclei we have 86 radon, that is 220. Clear? First I am talking about number A. In this case it is given to you 88, that is what, radium, and that is 226. Now let's suppose an alpha particle is emitted from this parent nuclei. So definitely the daughter nuclei that form 86, and we can say that will form, that is radon, and this is 222 plus, now you can say 2He4, this alpha particle is emitted, plus definitely some energy is also emitted. Clear? So in this question our objective is to find first the value of this Q. So Q value. Clear? How can we calculate Q value? For that one, first of all you will find that is mass defect, and it is multiplied with C square. Clear? You can also find this in terms of million electron volt. So 931 point, we can say 931 point, that is equal to 5. 931.5, this will you will find in million electron volt. Clear? So first of all we will calculate mass defect. How can we calculate? So for that one we can write like this: mass of reactant minus, that is, mass of product. Clear? Mass of reactant minus mass of product, and it is multiplied with 931.5 million electron volt. Clear? So now what is mass of reactant? Clear? Mass of reactant means directly you can say, actually some values are given to you in this question, and all these values are the values of atomic mass. Clear? But we will write here value of, that is, nucleus. Clear? So definitely we have to subtract mass of an electron. Clear? So directly we can write like this: mass of reactant we have, that is m, and we can see this will be 88, that is radium, and this is 226. Now we have equal number of proton and electron, so directly we can write this is 88 mass of electron. Clear? Then you can say we have minus, and what about mass of product? Clear? So mass of product means we can say we have, that is m of, you can say that is 86, that is radon, and we can say that is 222. Clear? Then definitely we have 86 proton and 86 electron, so directly we can write this is plus 86 electron. Clear? Yes. Now we have one more product, and what is that product? And we have alpha particle, so from that one we can write this is equal to minus. Clear? Yes or no? Yes or no? Minus. Now you can write like this: mass of, directly I am writing this is alpha particle, plus, now in alpha particle we have 2 protons, so definitely 2 electrons, so this is plus 2 electrons. Clear? Definitely we have to subtract these electrons in this one. Clear? So directly you can say this is actually mass of an electron. Clear? Mass of an electron. So now from that one you can see actually this 88 Me, 86 Me and this 2 Me, it will be cancelled out. Clear? So you will find actually whenever you are finding the positron, or you can say that is emission of an electron is to be taking place. In this case definitely you will find there is a significance change due to mass of an electron. Clear to you? Yes. So now from that one we can write that is Q value. Clear? So Q value, this Q value is given by now definitely mass of this radium. So this is atomic mass. Mass of radium, it is given to you that we have radium, this one 226.02540. Clear? So 226 point, clear, this is 02540. Clear? Then now we can see this one minus. Now if I am talking about radon, and that is 8622, so minus, this is what, 222 point, now 01750. Clear? Now what is mass of an alpha particle? Definitely you know this is equal to minus of 4.001506. Clear? Now it is multiplied with 931.5, and definitely you will get answer your in million electron volt. So from that one if you calculate, definitely you will get value, Q value, and this Q value you will get, this is 4.937 million electron volt. Clear everyone? So like this you can calculate Q value first. Clear? Second one, now our objective is to find kinetic energy of emitted alpha particle. So for that one first I am first telling you the concept. Now actually we know a relation between kinetic energy and momentum. Kinetic energy and momentum. So for that one you can see actually P square divided by 2m, this should be equal to kinetic energy. Clear? So whenever I am saying we have a parent nuclei, and in parent nuclei a deuterated nuclei is forming as well as alpha particle is emitted, it means now you can see there is no any external force is acting. Clear? It means we can apply conservation of linear momentum. Clear? So for that one you can see this momentum value, it remains same. Clear? So directly can I write like this: mass of alpha particle, kinetic energy of alpha particle, this should be equal to mass of, directly I can see mass of that is radon, clear, mass of Rn, clear, and kinetic energy of Rn, clear. Let's suppose this is equation number 1, clear. Now you know this Q value that we calculated, this Q value is actually provided to daughter nuclei as well as for the alpha particle. So we can write like this: kinetic energy for alpha particle plus kinetic energy for this daughter nuclei, this should be equal to Q value, clear. So now if you solve it, definitely you can find kinetic energy of alpha particle, because we have two equation and we can find two variables easily. So kinetic energy of alpha particle, it is given by, now actually we have a particular formula, directly you can find this is equal to Q multiply, clear, Q multiply, now you can see that is mass of radon, clear, and it is divided by, now mass of alpha particle plus again mass of this radon, clear. So now you can write it like this: kinetic energy of alpha particle, clear. So what is value of Q? This is equal to 4.937 million electron volt. Now what is mass of radon? Mass of radon, it is given to you, yes, this is equal to 222. So approximately I am writing this is 222 divided by, what is value of mass of alpha particle? I am taking that is equal to 4 plus this is 222, clear. So now we can write it like this: 4.937, this is equal to 222 divided by 226, clear, yes or no? Yes. So from that one, if you multiply 4.37 with 222 and 226, clear, you can easily get value of kinetic energy of alpha particle, and you will find this value 4.85, near about 4.85 million electron volt, clear to you? Yes, clear. Now actually we have one more part, this is only one part that we calculated. First we calculated Q value, second one we calculated kinetic energy of alpha particle. Similarly we have to find the same thing for the radon also, clear. So how can we write? Now let's suppose if I am talking about number B, clear, that is 86 radon 220. So 86 radon, this is 220. Now let's suppose an alpha particle is emitted. So when alpha particle emitted, this becomes 84, and 84 is an atomic number for polonium, clear. So this one, and definitely we have this is 216, clear, plus definitely an alpha particle is emitted, clear, plus definitely you will find some Q value, clear. Let's suppose I am saying that is Q dash. Now I will not write the subtraction of an electron, because definitely you can say, because there is no any positron is emitting, or there is no any absorption of an electron is to be taking place. So definitely you will find the same equal number of electron, clear, and they will be cancelled out at the end. So directly I can write like this: this Q dash, it is given by, now M, that is for 86 radon, this is 220, clear, minus, now we can say mass of 84, that is polonium, and this is 216, clear, minus mass of that is 2He, and that is 4, clear. So for that one, now mass of this radon, 86 radon, so for that one we can write 86 radon, where is this one? This one, clear. So that value you can write 222.01750, 222.01750, 01750 minus, clear, what is mass of this polonium, clear. So it will be given to you, that is equal to, actually you have this one is what, this is 86 or 88, that is important, that is 86, clear, okay, fine. Now you can say actually we have this one 84, clear, and this value you are getting 216.001, clear. So I am writing 216.001, clear, and it is multiplied with 89, clear to you. Now we are also subtracting 4.0086, for example, clear. Definitely we know 4 this one, that is 4.001506, clear. So I am writing that one 1506, clear. Now important part, actually we are talking about that is Q value, and this is only mass defect, clear. So definitely we will multiply it with 931.5 and we will get our answer in million electron volt, clear. So now we have to subtract all these values and we have to multiply it 931.5 million electron volt, clear everyone. So for that one, now you can see if you calculate all these values, you will find this value 6.41 million electron volt, clear. Now can we find kinetic energy of an alpha particle? Yes, kinetic energy of an alpha particle, it is given by, that is Q dash. Now then what is daughter nuclei? Means we can say mass of polonium divided by mass of alpha particle and mass of polonium again, clear. So for that one you can write it like this, Q dash. What about its mass? Mass is given to you, that is 216, approximately I am writing, that is equal to 4 plus 216. So finally I am getting kinetic energy for alpha particle. In the case, second case, you what is value of Q dash? Q dash value, that final I am getting 6.41 million electron volt, 6.41 million electron volt, and it is multiplied with 216 divided by, that is 220, clear. So now from that one we can write it like this, K alpha, this will be 6.41 multiply, now 216 divided by 220, so definitely this value you will get less than 1, clear. So definitely, let's suppose I am writing 0.99, clear. So exact value of kinetic energy of an alpha particle, that I am getting, this is equal to 6.29 million electron volt, clear to everyone. So like this you can calculate value, Q value, as well as the kinetic energy of alpha particle in both cases A and B, clear. So this is all about this question. Now dear student, we are going to discuss this question number 13.13, clear. And in this question it is given to you, the radionuclide 11 carbon decays according to, now one nuclear equation is given to you 6C11, it is now converting into 5 boron, then a positron is emitting and we have a neutrino particles, clear. Half life is also given to you and the maximum energy of emitted positron, it is given 0.960 million electron volt, clear. Now different mass values are given to you and now we have to calculate Q value and compare with maximum energy of positron emitted, clear to everyone. Yes. So now you can see, first of all, if we want to calculate Q value, clear. So definitely you know this Q value, it is given by delta mc square, clear. Or you can also write it like this, delta m means this is mass defect, and you can write it like this, multiply with 931.5 million electron volt, clear. So now our objective first is to find this mass defect. So can we calculate this mass defect? Yes. Delta m, this is given by mass of, we can say that is reactant, mass of reactant minus, that is mass of product, clear. So now you can say in this equation we are writing actually mass of this nuclei, and that is 6C12, clear, minus, now in the product side we have, that is mass of nuclei of, this is 5B11, clear, and we have one more, that is the positron. So mass of, directly we can say that is positron, so you can write it like this, this is E plus, clear to you. Yes. Now keep in mind all the values that is given to you, these values are in terms of atomic mass unit, clear. So atomic mass unit means we have to subtract mass of an electron. Now you can say, sir, why you are doing all this thing? Because in every question this mass of an electron is cancelled out. But my dear student, whenever you will find an electron that is emitting or an electron in the capture, definitely you will find some mass of an electron is to be taking place, clear. So now concentrate, I am writing delta m, clear. So this delta m, it is given by mass of nuclei 6C12, clear. So 6C, that is 6C11, okay, done. This is 6C11, clear. So now can we write, how can we write? We can write it like this, mass of, this is 6C11, clear, minus, now number of proton and number of electron we have same, so this is 6 times of Me, clear, this 6 times of Me, then minus. Now we can say nuclei, so how can we write? We can write like this is equal to mass of, and we can say 5 boron 11, clear. Now we have number of electrons and proton that is same, so we can write like this 5 times of Me, clear, and we have one more, this is what, positron, so you can also write it like this, this one equal to minus times of mass of an electron, clear. So now if you solve it, you will find this delta M is equal to mass of, this is atomic mass unit, you can write this one. Now you can say this is minus times of 6 Me and plus 5 Me, so this is equal to minus Me, so minus Me and minus Me, this is equal to minus times of 2 Me, clear. So minus, this is M, 5 B 11, clear, plus, or you can say minus 6 plus 5 minus, so directly you can say this is minus times of 2 Me, clear. So this is equal to minus times of 2 Me, clear. So this is total mass defect, clear. Now can we calculate value, Q value? Yes, definitely we can find the energy that is to be emitted, clear, and it should be equal to, now M, that is 6C11, clear, minus mass of, this is not in multiplication, I am just indicating mass of this particular nuclei, clear. So 5B11 minus 2Me, and it should be multiplied with 931.5, and you will get your answer in million electron volt, clear. So now we can place all the values. So first this value we have 11.01143, so 11.01143, clear, that is 11.01143, then minus, now I am saying this is equal to, actually this one is 5, clear, so 11.0093 minus 11.0093, clear, and now we can say minus times of 2 multiply, that is mass of electron, so definitely mass of positron, it is given to you, no, but do you know? Yes, actually we can write some value, you should keep in mind like mass of a electron or positron, so it will be 0.000548, clear, and it should be multiplied with 931.5, and you will get your answer in million electron volt, clear. So now if you subtract all these value, first of all you have to multiply, then you will subtract, so definitely you will get this value, it will be near about 0.00133, clear, and then multiplied with 931.5 million electron volt. Now you can say if we find near about value, so definitely let's suppose this is 0.001, so when we remove decimal, so this is 1 divided by 1000, so if you divide with 1000, so near about 0.9315 million electron volt energy you will get, clear. So final answer that you are getting, this is 0.96, clear, 0.96 and 2, this is million electron volt. So this Q value that we are getting, and because this Q value we are getting that is positive, it means I can say in this reaction some amount of energy that is releasing, clear. Yes, now we have to actually compare the maximum energy of a positron emitted, clear. Now actually now we can say definitely whenever we have this much of nuclei, when it is actually break down into these components, clear. So at that time you can say definitely this Q value is equally distributed, yes. So now I can say whatever this energy we have, listen very carefully, this Q, it is actually corresponding to kinetic energy of a daughter nuclei plus kinetic energy of positron, clear, positron plus kinetic energy of neutrino, clear, kinetic energy of neutrino. Now definitely we know if we compare mass of this daughter nuclei and mass of a positron, if you compare mass of this daughter nuclei and this mass of a positron, definitely we can say this mass is negligible compared to this one. So when the deuterium nuclei is very heavy, so definitely its kinetic energy will be very less, so we are neglecting. Now actually our objective is to find maximum energy of positron emitted. So for the maximum energy of positron emitted, we are assuming this is to be minimum. Clear? It means kinetic energy of this neutrino, this will be minimum, and let's suppose if we say this is near about 0, at that time you are getting maximum value of kinetic energy of positron. Clear? Kp, this will be near about q. Clear? So this value you are getting, it is equal to 0.962 million electron volt. Clear to everyone? So like this you can solve this problem. Clear everyone? Now student, we are going to discuss this question number 13.14. Clear? In this question it is given to you the nucleus, that is the neon 23, decays by beta minus emission. Now we have to write first beta minus decay equation. Clear? So we can write it like this, that is 10, this is neon. Clear? And that is 23. Clear? It is decays by beta minus emission, means definitely whenever we have beta minus emission, it means I can say atomic number is increases by 1 for the daughter nuclei, means I can write it like this is 11, and for the 11 we have that is Na, and definitely mass number will remain same. Clear? Similarly you can see antineutrino particle that will be emitted, and definitely some energy is also released. Clear? So like this we can write this nuclei equation. Okay. Now we have to determine the maximum kinetic energy of the electrons that is emitted. So it means we have to find this maximum kinetic energy of this beta minus emission. Clear? So now for that one, first we have to calculate that is Q, because this Q energy that is acquired by this daughter nuclei, this positron and this neutrino. Clear? Antineutrino. Clear? So now we can see how can we calculate this Q value. It is given by delta mc square. Clear? Or we can also write it like this, delta m into 931.5, that we are getting in million electron volt. Clear? So now from that one we can write like this, delta m. So delta m means we can say that is the mass defect. So first, can we calculate value of delta m? Yes, we can write like this, this is mass of reactant. Clear? Minus mass of product. Clear? Mass of reactant minus mass of product. Clear? So delta m, it is given by mass of reactant minus mass of product. So now we can write it like this, delta m, this should be equal to mass of reactant. Mass of reactant we have, that is equal to m, and this one that is 10 neon, and we can say this is equal to 23. Yes or no? Clear? Minus. Clear? Always keep in mind we will take here mass of nuclei. Clear? So now minus mass of product, so we can write like this, Mn, that is 11, Na, this is 23. Clear? And then we can also write like this, plus mass of, we can say that is beta minus, means minus 1 E0. Clear? And this one we are definitely neglecting mass of antineutrino. Clear? So now you can say how can you write like this, this is atomic mass of neon. Clear? Now we have 10 number of protons, so we have same number of electrons, minus 10 Me minus. Clear? This is what Mn. Now we can say 11 Na, that is 23. Clear? Then now first I will subtract. Clear? So I am not writing here N, this one. Clear? So definitely I will subtract mass of an electron. So total we have 11 electrons. Clear? Then you can also write like this, this is equal to minus times of, and we can see this beta minus particle is also having same mass as an electron. Clear? So from that one you can see minus times of 10 times Me plus 11 Me minus Me, means minus Me and minus 10 Me, this should be equal to minus 11 Me and plus 11 Me, this will be cancelled out. Clear? So from that one we can write it like this, M, that is 10 neon, this is 23. Clear? Minus M, this is 11 Na, that is 23. Clear? And we can see, yes, we have one more thing. Yes, that is clear. Okay. So directly you can say 11 Me and this one, that is cancelled out. Clear? Yes. So now we have this one is only for the mass defect. Clear? So now we can calculate Q value, and this Q value is given by delta M into 931.5 million electron volt. Clear? So for that one, now you can place, how can we write this value? So this value we are writing, that is equal to this one, 22.994466. So 22.99, clear, 44, and that is 66 minus, clear. Then I can see what is this mass, 22.98977, 22.98 and 9770, clear, this one, and now it will be multiplied with 931.5 million electron volt. Clear? So now if you subtract this, if you write here that is mass defect. Clear? So mass defect, definitely, can you subtract it? Yes, definitely you will find this value near about 0.00, and that is equal to 4896, and it should be multiplied with 931.5 million electron volt. Clear? So now if you calculate it, you will find this value near about 4.374 million electron volt. Clear? Near about you can say this is 0.0050. So if you remove this decimal, you can write 50 divided by 10 to the power 4 or 5 divided by 10 to the power 3. So you can say 5 multiplied with 0.931. Clear? So definitely you will find this value 4.374 million electron volt. Clear everyone? But what is my objective? My objective is to find maximum kinetic energy of that is electron that is emitted. Clear? So now you can say this Q value, it is actually giving kinetic energy to this daughter nuclei. Clear? Plus I can say that is beta minus, plus now we can say this one. Now our objective is to find maximum kinetic energy of electron. So definitely, because this daughter nuclei is very heavy, so we are neglecting kinetic energy of this daughter nuclei. Clear? And if we are taking this is minimum, kinetic energy is minimum for this one. Clear? So at that time you can say we are getting maximum kinetic energy of the electrons that is emitted. Clear? So now you can see kinetic energy of beta minus particle, that will be near about Q value. Clear? And that Q value you are getting, this is equal to 4.374 million electron volt. So this Q value we have 4.374, that is million electron volt. Clear? Q value we have 4.374 million electron volt. Clear to everyone? So this is all about this question. Clear? Now dear student, we are going to discuss this question number 13.15. Clear? In this question, first of all, definition of a Q value is given to you. How can we calculate Q value? So the Q value of a nuclear reaction, that is A plus B equal to C plus D, it is defined by Q equal to Ma plus Mb minus Mc minus Md, and it is multiplied with C square. Clear? Where the masses refers to respective nuclei. Fine. Determine from the given data the Q value of the following reactions and the state whether the reactions are exothermic or endothermic. Clear? So now first of all we are going to discuss the reaction number 1. Clear? Listen carefully. So I am writing first this equation, 1H1 plus, now this is 1H3. Clear? And then it is now actually breaking in 1H2 plus 1H2. Clear? Now if I want to find that this reaction is endothermic or exothermic, how can we find? So for that one I will calculate first Q value. If I am getting value of Q that is positive, it means this reaction is exothermic reactions. Clear? But if I am getting value of Q negative, so I can say that reaction is endothermic reaction. Clear? It means now we can say first, if we want to find Q value, we need what is mass defect. Clear? So first let me calculate what is mass defect. So mass defect, it is given by, now we can say mass of nuclei of 1H1 plus mass of this nuclei of 1H3 minus, now you can say because both are having the nuclei of deuterium, so directly I can say this is 2 multiply mass of nuclei of 1H2. Clear to you? So now you can say from that one we can calculate mass defect. So mass of nuclei, so listen carefully, all the masses that is given to you, this is atomic masses, so definitely mass of an electron you have to be subtract. Clear? So now you can say one electron, total 2 electrons, and 2 multiply to 2 electrons, so definitely masses of electrons will be cancelled out. Clear? So directly I am writing all the masses. So mass of 1H1, that is mass of a hydrogen. Clear? So you know what is that mass? Clear? Yes, actually directly we know positron, mass for a positron 1.0078. yes or no? Clear? 1.0078 plus what is mass of tritium? Mass of tritium is given 3.0160, 3.0, that is 160 minus 2 multiply what is mass of deuterium? Mass of deuterium, that is 2.014, so 2 multiply 2.014102. Clear? Now if you multiply it, you will find this value 1.0078 and plus 3.0160 minus, now multiplied with 2, so 4.028204. Clear? So from that one we can write it like this, this is equal to, if we add it we can say that is 4, 0 and 0, we can say 7, 6, so this is 13, so we have 1, this is 1, and we can say that is 8 minus 4.028204, and now this one. Now you can say if you observe it, you are getting this mass defect positive or negative, that is important for us. Directly I can say this is 0, and let's suppose from this one, so I can say 8, so 4, so this is 6. Clear? 13, this one we can say that is 5, we have 0, that is 8, and we can say that is 9. So 0.9856 I am getting, but this value we have that is negative. Clear? It means you can say this mass defect that you are getting, that is equal to negative. So this delta M is negative. So if I talk about Q value, listen very carefully what I am saying to you. If I talk about Q value, so this Q value, it will be equal to delta M into 931.5 million electron volt, so it will be also negative. Clear? So when we are getting Q value negative, it means this reaction we are having endothermic. Endothermic means we can say actually whenever these two that is proton and the tritium is reacting, actually we have to provide some energy to complete this reaction. Clear? So definitely this reaction is endothermic reaction. Clear? Now we are going to discuss number second. So in number second, it is given to you 6C12, 6C12. Now it is converting into 10 neon 20. Clear? So 6C12 plus 6C12, that is equal to I can say that is 10 neon 20. So 10 neon, that is 20. Clear? And now we can say that is alpha particle. So plus 2He, that is 4. Clear? 2He 4. So now we can say 6C12 plus 6C12, this should be equal to 10 Ne20 plus 2He 4. Clear? Now again the same objective, first we will calculate Q value. Clear? So Q value, that is given by delta M C square. So for that one, first we calculate delta M. Clear? Now you can see both are having same nuclei, so we can write it like this, that is 2 times of mass of nuclei of 6C12, that is minus, then minus. Now we can say mass of 10 neon 20, mass of nuclei of 10 neon 20. Clear? Minus, now that is equal to twice He4, so minus, this is twice He4. Clear? So from that one you can say, if we talk about total electrons, so 6, and that is we can say 6 multiplied 2, total we have 12 electrons, that is 10, and this is 2. Definitely again mass of electron will be cancelled out. Clear? So directly we can say value of delta M. Clear? Value of delta M that I am getting. So now we can say 6C12. Clear? 6C12. So what is this value? That is 12.000. So directly you can say this is equal to 24 minus. Now what is mass of nuclei of neon? This is equal to 19.9924. So 19.9924, and that is minus. What about helium? So for the helium, what is the mass? Clear? That you are having, that is equal to 4 point, this is 4.002603. Clear? And all these masses are in the AMU. Clear? So directly you can say this is 19, and we can say, so you are getting this value 24 minus, that is 23.9924, like this. Clear? So it means the most important part we have, that we are getting this value positive. So whenever we are getting this delta M positive, it means Q value, if I am talking about Q value, so Q value definitely this delta MC square, this is also positive. So in the second case we are getting Q value that is positive, it means this reaction is exothermic. Clear? This reaction is exothermic. Clear? Exothermic. Clear everyone? So directly you can say this reaction we have endothermic. Clear? And this one is what? That is exothermic, because we are getting Q value positive, means definitely energy of a reactant, it will be more compared to energy of products. Clear? That's why we can say in the second reaction energy is releasing, but in the first reaction we have to provide some energy if we want to conduct this reaction. Clear to everyone? So this is all about this question.